Hello, everybody. Thank you so much to the organisers for inviting me here to talk to all of you. I'm really excited to finally be visiting Austin. I've heard a lot about this city, and I'm very happy to be here. I'm going to talk to you about the work that I've been doing to try and understand the atmospheres of other planets. And this comes down from two really big questions in astronomy. How do stars and planetary systems form? And is life unique to our planet? Those are huge questions. And there's a big void between those two questions that involves many different processes, many different aspects of astronomy, and many questions we need to answer along the way. We can look at our own solar system of planets and see that there is a huge diversity out there. There is a large array of different types of atmospheres, different types of structures, different types of worlds. And that's just around one star. So if we start looking out across the other stars in the sky, what do those worlds look like? What are the differences that we're seeing across all of those worlds? Since the early 90s, there have now been over 4,000 worlds discovered orbiting other stars in the sky. And these are all mostly incredibly local to us in our galaxy. So imagine expanding this out to further reaches of our own galaxy and to other galaxies that are in the universe. There are thousands, hundreds of thousands, millions, billions of planets out there. And we can use those different planets to try and understand our own solar system. What you're seeing here is the planets that have been discovered and the different methods you can see on the side there. Their distance from their star versus their mass, so how massive are they? And I've put the solar system on there as well, so you can see the types of worlds that are being discovered are not like our solar system planets at all. So they're going to be answering very different questions. They're much closer to their star, most of them much closer to their stars than Mercury is. And they're also much more massive. They're more on the size of Jupiter, Saturn, Uranus, Neptune. These are large worlds orbiting very, very close to their stars. We need to try and understand a lot more about them. But to do that, we need information, and information is difficult to get. Primarily, we need to understand their mass and their radius. So we need both the mass and radius so we can understand the density, the bulk density of these planets. And what you're seeing here is I've now grayed out everything that doesn't have both of those measurements. In black are left the only ones where we've got both of those pieces of information. And you can see in this red line here, there's this gap that we're seeing. This gap is not fake. This is a real gap in the types of planets that are being discovered. You can't get planets this size, it seems, that close to their star. But as you go smaller, you can, and as you go larger, you can. So there's a lot of information just alone in this diagram. But what I'm going to do is I'm going to take you through these planets, these black planets right here. And the reason why we've got this information on their radius and their mass is because we're able to measure them as they pass in front of their star. So from our perspective, these worlds are passing in front of their star, blocking out a small portion of the light. And what we're able to do is measure the relative size of that planet compared to the size of the star that they're orbiting. We can also measure their mass through the Doppler method. So this is looking at the shift in the spectral lines of the star itself as it's being pulled by that planet. So these two bits of information give us the mass and the radius of that planet. And the beauty of the transit method is it also gives us the inclination of the system. So with the Doppler method, that information on the inclination, so the orientation of that system, is tied into the mass that you measure, the pull on the star. But the transit gives us that information. So you can really disentangle these two things and have a really accurate, nice measurement of the mass and a measurement of the radius of the planet. And what you can do is you can then put them on a mass on the bottom here versus radius diagram. And you can see these different sections I'm showing you, the giant planets at the top, down through to these much smaller Earth-sized worlds. And if I put our solar system on there, the diagram looks very different to what we saw before, where none of these worlds look like our solar system planets at all. Now our solar system planets sit right in that distribution, looking at this mass radius of these worlds. So we've got a nice array of around 300 or so worlds that we have this information for, and we can start to try and pick that apart and understand them a little bit more. So we come back to those big questions, and we have to break it down even further. What we want to know is, what are the atmospheres of these worlds like? Are they like or unlike our solar system planets? What are the clouds in these atmospheres? How are they going to affect our planet, and how are they going to affect what we're measuring? And I'll show you some of that in detail later. And can we trace any of this information back to that original question? How do these stars and planets form? Can we trace any of that information we're measuring? So I want to take you through these different questions. First, I'm going to show you a bulk of the work that we've been doing, trying to understand what the atmospheres of these different worlds are like. And I'll take you back to this mass radius diagram, but now what I've done is I've added on lines which show you the theoretical composition of these worlds. So you've got the bulk density of these worlds based on their mass and radius, and these lines are showing you different potential compositions of those worlds based on those two properties. And what you can see here, we've got some rocky, icy worlds that follow these lines here. And then we've got the pure hydrogen helium. These are gas giants, just like our solar system gas giants, dominated by hydrogen and helium gas in their atmospheres. And then there's this big gap in the middle where our own ice giants sit. Our own ice giants, Uranus and Neptune, are a little bit of a mystery to us still. And it's really important that we try and understand this portion of the diagram, because we don't have that information in our own solar system. And what you can see here is, if you look down at the small end, the distribution of the types of planets that we're seeing. So if you look at that diagram, you break it down, we've got our giants up here. There's actually very few of them. This is just a histogram of the number of planets in those size ranges. There's very few giants out there. There's quite a lot of rocky worlds. So worlds mostly composed of rocky materials likely have a very thin atmosphere. But there's this big gap in the middle here where you can see that histogram spiking. We don't know what these are. We do not have the equivalent in our solar system. The most abundant world in our galaxy, and if we propagate that forward into our universe, are these planets which are somewhere between the size of the Earth, a rocky planet, and Neptune, a gassy planet. And we don't have that in our solar system to tell us at what point in this diagram you transition from a gas world to a rocky world. Where does that happen? Is it a nice linear process? Does at some point in this that just happen? You lose all your atmosphere and you are a rock? We don't know. And if I take you back to that first diagram I showed you, where these worlds that we're studying are much closer to their star, we have completely different questions as well. What happens when we stick them right next to their star? They become hot Jupiters, Jupiter-sized worlds very close to their star, heated to over 1,000 Kelvin. We've got warm Neptunes. We've got evaporating worlds in the middle, where you've got these planets really close to their star that are being bombarded by stellar radiation, and they're losing their atmosphere. And we end up with, in the rocky bit, lava worlds, planets with full magma oceans across their daysides, and stripped cores of planets that potentially had much larger atmospheres. So we're talking about some very interesting situations here. So how do we look at our atmospheres and try and work out what we're seeing? So this is just showing you the cyclical process that occurs to try and understand a planetary atmosphere. We take our measurements, we have to break that up into lots of different colors, into our wavelengths, and we're able to measure the atmosphere. I'm going to show you some of this in more detail soon. But it's not just important to measure them. We have to understand what we're looking at. If you just take those data points without that nice blue squiggly line behind it, it means absolutely nothing. We need the theoretical side as well. We need to understand the temperature structure of these atmospheres, the clouds in these atmospheres, the chemistry that is happening, and the circulation. If we bring that together, we can start to interpret what we're seeing. And this is an iterative process where we loop round and round and round to try and really hone down the nature of these alien worlds. So I'm going to really show you something called transmission spectroscopy. What you're seeing here is the relative size of the planet that we see with a function of wavelength. So as we change the wavelength of light that we're measuring, if there's something in the atmosphere like sodium, the planet will absorb that light. The atmosphere of that planet will absorb the light from sodium, and it will appear bigger to us. It will block out more light. So the relative size of the planet will change with wavelength. So we can actually measure the relative change in the size of the planet with wavelength, and each different molecule has its own unique fingerprint. So sodium has a unique fingerprint, potassium does, water, CO2, carbon monoxide, they've all got their own little signatures in wavelength space that we can disentangle from this relative size that we're measuring of the planet as it passes in front of the star. And we need to do this over many different wavelengths for multiple reasons. Different molecules absorb in different wavelengths, but also different wavelengths penetrate different areas of the atmosphere. They can go deeper, so if you've got visible infrared light, you can go deeper into the atmosphere, looking at different areas or pressure layers in the atmosphere. We also need to go out to the UV so we can start seeing the very extent of these atmosphere, the very edges of the atmosphere where the star is having the biggest effect on that planetary atmosphere. And you can see also that it changes the chemistry and the temperature structure. So what I'm going to show you now is some of what we expected to see and some of the results that we actually saw when we used the Hubble Space Telescope to look at these atmospheres, to measure that relative change in the size of the planet over wavelength. We looked at 10 giant planets over a range of temperatures. And if we line those planets up in terms of temperature, what we expected to see is a nice change from our molecular signatures here. We're seeing that sodium and potassium there, those big spikes in the optical, they start to disappear as something called titanium oxide and vanadium oxide takes over in the absorption profile of the atmosphere. We expected to see this nice trend from hot to cold atmospheres where the signatures that you're seeing correlate with the temperature structure of that planet. What we actually saw was something very different. You have to reshuffle this quite considerably. What we measured was actually no correlation whatsoever with the temperature of the planet. What you're seeing here is the measurements that we made with the Hubble Space Telescope in the black colored points and the models in the background that I'm showing you here on the side. What we saw was a continuum from clear atmospheres with these strong molecular signatures to cloudy atmospheres where you can't see any molecular signatures at all, or there's this really strong slope. But it didn't correlate with the temperature like we expected it to. So the chemical signatures in the atmosphere that we're seeing is not responsible by temperature alone. We also have to think about other things. So what's happening in these atmospheres? We're seeing this nice continuum from clear to cloudy. What does that even mean? What does this cloudy part mean? There are a lot of particulars when measuring an atmosphere. It's not just about what you're measuring, it's about the amount of information you can get from that. So we got really nice, precise measurements with Hubble, and that's fundamentally because we're looking through a huge amount of atmosphere. These are gas giants. These are hydrogen-helium-dominated worlds, very close to their star. We can get a lot of photons that pass through that atmosphere before reaching us. And you can see here, relative to the size of a Neptune-sized world or a temperate, Earth or a rocky world with a small atmosphere, it's not impossible, but it's more difficult. So what we're seeing is these large worlds, but we're not seeing what we expected. We can push down to smaller worlds, and we have been. It's been a lot of work, but we've been pushing down to smaller and smaller worlds to try and understand if this continuum keeps going as we go smaller. Is it unique to hot Jupiters? Is it unique to these giant worlds? Does it continue down to these smaller worlds? What you're seeing here is a continuation of that diagram from smaller Neptune-sized worlds right down to things that are roughly 2.5 times the size of the Earth. So we're still seeing this continuum from clear molecular features in the atmosphere to cloudy features. And we've actually looked over 37 different planets now with the Hubble Space Telescope, and what we've understood is that there is a distribution in the amplitude of the water absorption feature specifically, which happens in the near infrared, where we can measure that there is a muting effect in these atmospheres. There's something in these atmospheres which is causing the water absorption feature to be smaller than we expected. And we're seeing that actually 80% of the planets that we look at have water absorption in their atmosphere. We're seeing that, but that it's muted. So just to really kind of show you what I mean by this, this is a typical transmission spectrum that we would expect to measure for a planetary atmosphere. You can see the different molecules indicated on there. We're looking over these two different ranges. That's what I showed you were these two Hubble Space Telescope ranges. We have lots of data on many different planets across these ranges. But what we're seeing is the effect of clouds in these atmosphere. And clouds that are made of large particles will block light uniformly across all wavelengths. So what they're doing is they're cutting off these features uniformly across all wavelengths. But really nicely, the nature of light and particles, if you've got small particles, they interact with light differently. They scatter in short wavelengths. They have a wavelength dependence. So as you go to the shorter wavelengths, you'll start seeing this Rayleigh-like scattering. So the sky on Earth is blue because we've got scattering by small particles. This is slightly different, but this is just scattering by these particles that are forming the clouds in these atmospheres. And we're seeing the effect that it has on this water feature. If we zoom in on that very specific water feature that we're measuring with Hubble, you can see that's what we would expect at 100%. But what we're measuring is roughly this 33% feature, because there's clouds in the atmosphere that are either scattering the light or uniformly absorbing that light. So the big question we have here is, what are these clouds made of? And this is the question that I really like to ask, because it's a really interesting one. I've just shown you the scattering effects versus the uniform effects of these clouds. And if you have different amounts of the clouds or different wavelengths that they're affecting, you can see they have very different effects on those features. And this really just comes down to fundamental physics. It is looking in the Rayleigh regime, where you've got this small wavelengths, small particles. What we're looking at fundamentally for these exoplanet atmospheres is in the Mie regime. The Mie regime is where your wavelength is equal to the size of your particles. So you're seeing these different scattering effects. But the fun part comes in realizing what these clouds are made of. If we look at our solar system, they're over here. These are nice cold planets. We have clouds that are made of water here on the Earth. They're all over Britain. I think that's probably why I love clouds. We've got colder, even colder clouds as we go out to our giants. We've got methane, ammonia clouds. But the planets that I'm talking about are much closer to their star. I said they're over 1,000 Kelvin. We're talking about clouds made of incredibly different substances. We don't have our nice clear waters and ammonias. We instead have disodium sulfide. We have something called enstatite, which is sand, glass. We have different kind of gems and jewels that form rocks here on the Earth. And one of my favorites is a thing called corundum, which is the basis of sapphires and rubies. And these are forming the clouds in the atmospheres of these planets that we're looking at. They're scattering that light in a very specific way where we can try and understand a little bit more about the structure of these planetary atmospheres. And this isn't unique to exoplanets, beautifully. It's across all different astrophysical phenomena. You can see it in the ISM, you can see it in galaxies, you can see it in protoplanetary disks, you can see it in brown dwarf atmospheres. These materials are known. These materials have been measured throughout all different astrophysical phenomena. It's dust particles. We know they form. So this will be one of the first things that we will be testing to try and understand if this is what's happening in these planetary atmospheres. Now, the next slide is completely unscientific in the graph, but I like it. This absolute mess that you're seeing here is what these types of materials, so we've got a huge list of different materials there, would do if you shone light through them. So it's scattering light. So put them in a planetary atmosphere, you give them a particle size and a distribution, so form a cloud, and you shine that light through it. And what you're seeing here is the fundamental vibrational energy of that molecule. So the main diatomic bond in that molecule, so between, say, silicon and oxygen, that vibrational mode between those causes this very distinct absorption feature. And you can measure approximately where that will be, just based on fundamental physics. And this is just a smattering of all the things that we might expect to form clouds in the atmosphere. And you can see there's a huge amount of information that is ready for us to pick apart. But right now, we're only measuring in this very short regime with Hubble. The Hubble Space Telescope goes out to 1.7 microns. We're only measuring that portion of the regime where it's still scattering that light. It's not making these large, beautiful vibrational mode features. So what we need to be doing is using the information from those scattering slopes to try and constrain what kind of size particles we're looking at. I showed you uniform versus scattering. What you can do with that is you can back out a range of particle sizes you would expect. And based on that range of particle sizes, you can estimate what those vibrational modes might look like. And we can go looking for compositional information of these clouds. We can prove, hopefully, in the future, that this planet here has clouds that are made of rubies and sapphires. I think that's pretty interesting. But just to show you again what this means on this diagram, we come back to those scattering versus uniform clouds. If we stick on something like enstatite, so enstatite is sand, it's glass, so liquid glass or solid glass particles in the atmosphere forming clouds, you can see we can fit that scattering slope really nicely. This is a 0.1 micron size particle. And you can see that vibrational mode comes right above the gas phase modes that we've got there. So we should, if it's there, if our clouds are made of this material, be able to measure that with the James Webb Space Telescope. And you can see that the shapes that we've got there all change and all give us different bits of information about what's happening in this planetary atmosphere. So one of the final questions that I said was, can we take these back to planetary formation? Can we understand, based on these atmospheres, how they formed or evolved over time? Now, there are two different ways that we can look at these atmospheres. We can measure the ratio of elements, so oxygen to carbon is a really good ratio that we can measure, because it's thought that as you form in a planetary disk, as you move further away from the star, you have these ice lines, points in which different gases condense out. If you form beyond one of these ice lines, you should have the information embedded in your atmosphere, in your composition, this C to O ratio of where you formed in that disk. So we want to be measuring the amount of water, which is oxygen-containing molecule but no carbon, to, say, CO2, where it's got that carbon information in there. If we can measure the ratio of our different molecules, we can start to try and understand, potentially, where in their disk they formed. But there are also two different types of formation scenarios that we have to consider. One is just gravitational instability, the same way that stars form. Do planets form in the same way that stars do? They just collapse under gravity. And what that would mean is that they have the same atmospheric metallicity as their star. They would look very much like their stars. Or do they form by clumping of dust? Do they form by core accretion? Do they clump and then accrete gas and then go with runaway accretion within their disk? And that would mean that they would have a trend of more metallicity, the smaller the mass of your planet. So more metals, the smaller your planet. So there are two different things that we can measure there. But when we put that in terms of the types of planets that we're looking at, it becomes really complicated. If you change the metallicity of your planet, you change the amount of water you would expect to see, you change the scale height of the atmosphere. The more heavy elements in your atmosphere, the more dense your atmosphere, the smaller the extent you expect your atmosphere to be. So there's a hugely complicated phase space that we have to disentangle. And how we do that is really important. We do that with lots of information across lots of different wavelengths. And one of the ways that I can show you this is showing you just information that we've got here for one of these planets. What you're seeing here is three very distinct water absorption features in the near infrared. You see those three bumps there in the data. If you measure that data and you use models to try and interpret what you're measuring there, you can see the distributions that we've got here. we're really not constraining the C to O ratio at all. The metallicity is also a very broad distribution, so it's very difficult to understand what's going on here. But if we add in extra information, we start to narrow it down. And if I just compare those two for you, you can see that the extra information we're getting is really helping us constrain those clouds, helping us understand the scattering properties of the atmosphere, which has really helped us understand the temperature a lot more. So the types of clouds that we're forming, the temperature of that planet, and we're able to much better understand what the C2O ratio and metallicity of this planetary atmosphere is, because we've got more information over a wider wavelength. And I think one of the really important things here is that we can compare this type of thing to our solar system. If we look at our solar system, we see this trend, this core accretion trend. The larger your planet, the lower the metallicity, or the smaller your planet, the higher the metallicity. Neptune and Uranus are around 100 times the amount of metals, heavy elements in their atmosphere compared to the Sun, and Jupiter around 4 times. What we're seeing, what we're measuring with exoplanet atmospheres, however, is a bit more of a mess. There's a lot more scatter in there. It's a lot harder to disentangle. So is our solar system unique in the way that it formed? Is it like all of the other systems that we've got out there that we're studying? That's one of the big questions we're trying to answer. But those figures that I just showed you, as we increase the wavelength range, if we go out to the James Webb Space Telescope, which will be launching in 2021 at some point, it will be, it has to. You can see here, for this planet that I just showed you on that purple and green diagram, in the background in gray, you might not be able to see it very well, is the Hubble measurements that we made. If we take that model, that best fit model, and we propagate it out to different wavelengths, and then we simulate what we should measure with the James Webb Space Telescope, you can see in this histogram at the end here, the big blue region in the background, that's what we constrained with Hubble. And I already showed you, those are pretty good constraints. With the information from the James Webb Space Telescope for this planet, we would know very precisely the metallicity and C to O ratio of this planet. And that mostly comes from this region here in red, where we're able to measure carbon dioxide and carbon monoxide signatures in this atmosphere, something that we cannot do currently with the Hubble Space Telescope. So it's going to be really interesting. One of the biggest things that we're going to be doing in exoplanets is looking for carbon species in exoplanet atmospheres, where we've really been limited to water at the moment. So a little pun just to finish us off. Where do we go from here? Not biased in any way whatsoever. Just a quick look at what James Webb is already going to be doing in its first year of operations. A large fraction, 27% of GTO guaranteed time on the Hubble Space Telescope, which is awarded to teams across the world that have been working on the telescope for many decades now. 27% of that time is going to study exoplanet atmospheres, trying to understand these worlds, trying to understand the things that I've taken you through today. And you can see across that mass radius diagram, the smattering of those worlds filling in that space, vitally filling in all of that phase space, right down to these small rocky worlds in yellow at the bottom there. So we're going to get a huge amount of information from James Webb in its first year alone. And we also have a large exoplanet community have come together, and we were awarded 78.1 hours of Webb time to really study in detail one hot Jupiter, get all that information I showed you, and how that's going to change the way that we understand these planetary atmospheres. We're going to be measuring a full phase curve of a planet, trying to understand the temperature structure of that planetary atmosphere. And we're going to be testing the limits of the telescope itself. We are going to be pointing it at a nice bright star to test the limits of the precision that we can get in these atmospheres. The more precise we can get, the better. The more we understand these instruments, the better. And I'm also very lucky to be part of one of those GTO programs that I told you about, where we're going to be getting a census of 3 different worlds, 1 giant planet, 1 Neptune-sized world, and 1 terrestrial world. And we're going to be looking across the entire spectrum of those worlds to really try and pick apart and understand them. And this will form what we're calling the Rosetta Stone of comparative observations so that all other planets and measurements that we make can be compared to this full transit spectrum, and try and understand which regions of the spectrum are the best to use. So I'm going to end with a couple of takeaway points that I hope are interesting to you. The metallicity C2O ratio, cloud opacities, these are all playing huge roles in these planetary atmospheres, and they're intermingling with each other. It's not just about the temperature. Temperature changes your chemistry, but there's a huge amount of other things that are affecting it there. If we can combine information from multiple telescopes across multiple wavelengths, then we can get really, really detailed data points, and we can start to disentangle these processes, because right now they're in a bit of a mess. And every single one of these methods that I've shown you today, I've shown you giant planets, but we've already been using these to study smaller planets, smaller worlds, things like the TRAPPIST-1 planetary system, which is 7 Earth-sized worlds around a very small star. We've already been using the Hubble Space Telescope to try and understand these worlds in the same way that we've been doing for these giant planets. So these techniques, everything that we're doing, will be used in the future to try and answer that other massive question we have. Is life unique to our planet? And also, in the spirit of Frank Bash, I run a podcast called Exocast. Exocast is an hour-long podcast released every single month. Please, if you want to know anything about exoplanets, we cover a huge number of things, but more importantly, we have something called the Exo Cup. If you are on Twitter, the Exo Cup is a knockout competition between exoplanets. They will compete against each other to determine which of these planets is the greatest of the exoplanets. We've had 2 years running of this. We've had a varied array of winners. People seem to like the hottest ones, so we'll see if we can change that this year. But we have 32 worlds. 24 of those worlds were selected based on the number of mentions they had in publications this year. So it truly is the competitors against each other. So please, if you are interested, follow Exocast and learn about these knockout worlds. Thank you.
Okay, questions for Hannah? Great.
Okay, so for this Rosetta Stone project, you're sampling the different categories, but you've also said that the diversity and appearance of the atmospheres is driven by you've also said that the diversity is driven by how cloudy or hazy it is. So are your 3 template representative objects similar in terms of clarity versus haziness, or is that actually going to be the primary differentiation between those Rosetta Stone?
That's a fantastic question. So if we're recording online, you need that. The question was, out of the Rosetta Stone that we're setting up, are these clear, cloudy? Do those differences that I mentioned at the beginning matter? And the beauty of the planets that we selected are they all show water absorption features in the infrared, but they also show slightly different properties. So the hot Jupiter has a scattering slope, and this suggests that there are small particles forming clouds in the atmosphere, and the wavelength dependence of that slope should disappear as you go into the infrared. So those absorption features by the gas species should become the dominant portion of that atmosphere. So what we'll be able to do for that hot Jupiter, which I find incredibly exciting, is measure that wavelength dependence of the scattering for those clouds. And that wavelength dependence is something that we don't have a solution to right now because we aren't going far enough into the infrared. For the warm Neptune, there is suggestion of actually a more uniform cloud particle, larger cloud particles in this atmosphere. So for that one, what we'll be able to determine is if at longer wavelengths there is a wavelength dependence. Me theory suggests that for the types of particles that should be forming these clouds, it should also drop off, but at much longer wavelengths. We'll be able to determine from this exactly what point that is, and again try and understand if these clouds are affecting the atmosphere. And to be honest, for the terrestrial world, we got no bloody clue. We don't know if it has an atmosphere at all, but we're going to look and try and find out. We genuinely have looked at this planet with the Hubble Space Telescope, and we've been able to rule out the presence of a large, clear hydrogen envelope around it. But this is a world which is 1 Earth mass and 1 Earth radius. We expect it to be rocky. We just don't know if it's got an atmosphere. So that one's really going to be a brand new information.
Other questions?
This one might be a little technical, but I'm doing a project right now on plasmineralogy, and I was wondering, in your opinion, what the lowest temperature that will condense corundum. So essentially, what the lower effective temperature cutoff is.
So the question was, what's the lower temperature cutoff for corundum, which is that rubies and sapphires base I was talking about. So corundum is very much the hottest material. It also doesn't very easily spontaneously form. So you've also got to think about the energy required for something to spontaneously condense. But corundum we expect to be forming in the atmospheres of planets that are between 1800 Kelvin up to about 2100 Kelvin. However, we've also got to consider the fact that the most easy thing to form clouds in these atmospheres is enstatite and forsterite, these magnesium silicate sand materials. That does spontaneously form very, very easily. It has the most abundant elements also form it. So magnesium and silicon are the most abundant. Aluminium is not nearly as abundant as those two. So you're going to have far less of it. So we've also got to consider the fact that these more dominant species that we expect to form clouds might be masking some of that and taking some of that oxygen material as well. So there's a big balance between all of these. One of the things that I like about the planet that I showed you, and I'm actually going to be talking about it at Astronomy on Tap tonight, is that it's incredibly hot. It's 2,500 Kelvin. It shouldn't have any clouds whatsoever. Nothing should be able to form solids or liquids in that atmosphere. But we see very strong evidence of these clouds at the limb. What that's telling us is that the heat is not being transported from the day side to the night side of this planet. That heat is not moving around. So it's not that hot. It's actually getting much colder. So we've gotten information just from that alone about the temperature of this planet and the way that it's structured. But at that high temperature, because we don't expect anything else to form, it actually limits the phase space of the types of materials you can be looking for. It limits what kinds of materials could possibly form these clouds, and therefore gives you a little bit less to be having to disentangle from the information that you're getting.
Thank you. Any other questions? Yeah.
So I have a question about what James Webb will be able to do. So you showed how, like, with this additional wavelength coverage, you'll be able to better constrain the models that you're currently using.
Mm-hmm.
So my question is, will it be able to put maybe weaker constraints, but on more complex models that have that tell you like some different physical insights than is currently possible with data that we have?
So the question was, the James Webb Space Telescope data is going to help us try and constrain the models that we've got, but can it place weaker constraints perhaps on even more complex models? So one of the things that we're looking into at the moment and trying to piece together is lots of different information. These planets are not one-dimensional, they're 3D. They have a permanent day side looking at their star being heated up and a permanent night side. And the effects of that are very three-dimensional. There's horizontal winds around these worlds. There's vertical mixing, convection versus the radiative portion of the atmosphere. There's a huge amount of information in there that is very difficult to disentangle. One of the things that we're hoping to be able to do, because we're going to much different wavelengths, and I showed you that diagram at the beginning, we're probing different regions of that planetary atmosphere. So the deeper we can go into the atmosphere, the more we can try and understand about these different boundaries that we're talking about, these different pressure boundaries, where the temperature potentially turns over, where you've got inversions perhaps in the upper atmosphere. We're starting to try and understand those a little bit with the Hubble Space Telescope data that we've got, but what James Webb's going to be able to do, giving us this full gambit of information from the optical all the way out into the mid-infrared, is going to be able to tell us more about that vertical structure in the atmosphere, but it's going to be a difficult one. That's going to be one of the things that's so hard to disentangle, and it's going to take a lot of work, but I think that helps answer that question.
Any last questions? Yeah.
So the question was, the smaller planets in our solar system show very, very thin atmospheres. And how similar are the ones that we're probing? What are the limits of what we're going to be able to do for these small worlds? So I showed you at the beginning, the measurements we're making are relative measurements to the size of the star. So the size of the planet is measured relative to the size of the star. So the smaller the star we look at, the smaller the planet we can measure that has the same effect on that light. So that's really primarily what we're doing right now with these smaller worlds that we're looking at are around M stars. They're around very cool, very small red stars. One of the advantages of M stars is that there's way more of them than there are G-type stars. So there's a lot of places to look. The measurement is much easier. But the environment is completely different to what we have in our own inner solar system. So for the transiting method, for the method that I've talked about today and looking at the atmospheres like this, we're really not going to be able to probe things like the Earth around a sun-like star. For that, you would need advances in direct imaging methods so that you can block out the star's light and see the light coming directly from the planet if you want to see an Earth around a sun-like star. But for the planets that we're looking at, we can see the atmospheres and measure the atmospheres of these worlds around these much smaller stars, but we do have to make considerations for what the environment's like there. These stars give off huge amounts of flare energy. They give off a very different set of wavelength of light compared to the Earth. So what does that mean for biology that might exist there? What does that mean for the atmosphere, the composition of the atmosphere? The mass of the disk alone, when you form these planetary systems, is so much smaller than the disk that formed our own solar system. We still don't fully understand exactly that process. And for the TRAPPIST-1 planetary system that I've studied previously, which is 7 Earth-sized worlds around a very, very small star, some of the different simulations for the planet formation have shown that it has to be 120% efficient to form that planetary system. So we still don't quite know how they form. So there are huge differences between these small planets that we're talking about around these small stars with transits and transmission spectroscopy. But I would say, I'm a skeptic. If you listen to Exocast, you'll hear that I'm the skeptic of the lot. Give us 100 years and we'll have maybe a bit more. I don't know. And direct imaging, I think, will be an excellent way of doing that kind of thing.
Stay tuned. Okay, any last questions? Great, all right, well, thank you again.